one starts with a Laplace transform, and particularly thinking Laplace transform for circuits, but it could be for many different things. There's a number of interesting properties that allow us to start talking about how does this relate to things like frequencies and sinusoidal inputs into the system. And we start to notice that there's this additional approach called a Fourier transform, which is very similar to a Laplace transform. And in fact, you can kind of almost derive one from the other. Now, if you're being really rigorous, you have to be a little more careful than this. But what you find is you start with a Laplace transform formulation, that integral, and S is going to be a complex structure where you're doing this both over frequency as well as over real elements. And you have this sort of transformation that you go into Laplace transform and out of Laplace transform. Well, it's an interesting concept of talking about what is a Fourier transform. And Fourier transform actually has an integral that looks very, very similar. It looks very much as if I pretty much just made sigma equal 0, so I'm only making S into j omega. And again, remember j is square root of minus 1. And I actually have a reversible transform. So things going in one direction, I get the same transform behavior in the reverse. There's sort of this reversibility into the structure. It is a slightly different because it integrates over infinity to minus infinity versus 0 to infinity. But basically, they're very, very similar concepts. And in fact, in many cases, we can kind of very quickly get to Fourier transform behavior in our circuits. Particularly, remember, we can talk about our circuit elements as being kind of like resistances, but in S domain. Well, I can start to do some stuff in the Fourier domain, and this starts to get really, really interesting. Now, for those of you who looked at Fourier transforms carefully, you'll realize that they are extremely critical for all sorts of signal analysis. They're extremely important in quantum physics because it turns out momentum relates to the Fourier transform position, and it's really related to the wave behavior of particles in that space. And so that in and of itself gets to be quite interesting. And there's some interesting intuition and analysis there. But when you look at it from the circuit perspective, what's intriguing is you can say, let me talk about my circuit, which is just an RC first order structure, has a transfer function, gives you 1 over 1 plus S tau. Well, you might say, well, I'm curious what the frequency behavior is. Well, I can just sort of take S and make it be j omega, so basically get rid of the imaginary part of it. I'm kind of moving to a space that feels like a Fourier transform. We're kind of in an interesting limbo sort of space, but we can kind of think of it that way. And so you can kind of talk about omega. You may say, well, how do I get from omega to frequency? Because omega's angular moment is sort of not angular momentum, but it's in radians. And so when you look at this, you're saying, okay, so now it's 2 pi times f. So that's how you get frequency out. What I would need to then just simply do is then substitute S for j omega, and I get 1 over 1 plus j omega tau. Certainly this is a complex result. It turns out this is complex too. We just didn't think about it because of the S, but both of them are complex. And so a lot of times we'll ask the question then, well, what is the magnitude, what is the phase? And you can actually directly calculate that. Of course, we know that the magnitude is A plus JB would be just the square root of the sum of the two. We know phase is an inverse tangent of the imaginary over the real, so you get sort of tan inverse of omega tau. And then we can start to plot and sort of look at these things in frequency. And this turns out to be really valuable in terms of to approach this. But what's also interesting is that, again, I started with a whole circuit approach. I started with the fact that I can actually make the sort of state holding elements now look like resistive elements. And then from that, I can immediately sort of look at frequency. And this turns out to be quite powerful techniques to be able to analyze structures, because we often like to use sinusoids and various frequencies in our analysis, and this gives us an opportunity to do this in a very direct way without ever touching the differential equations if that's how we want to approach the problem.